video. Today we're going to be looking at ways of counting. We're going to look at the number of possible outcomes from a series of probability experiments. We're going to look at the number of ways of choosing a set of objects, and then there's some associated probabilities that we want to connect these counting methods with. So let's consider one problem here. And the problem is you're making a sandwich. So you arrive at a friend's house for lunch and you're invited to make a sandwich from food laid out on a buffet table. To make the sandwich, you need to choose one type of bread, and there are 3 to choose from: whole wheat, white, and pita. You need to choose one protein, and you can either have tuna, salami, roast beef, or turkey. And then you need to make another choice. Are you going to have lettuce? Or are you going to choose to not have lettuce? And are you going to put tomatoes, or are you going to choose to not put tomatoes? So those are 4 different choices. And the question is, how many different sandwiches can you make? Okay, so this is a little complicated. We're going to start with an easier example. So, and then we'll come back and count out the sandwiches. So in this next example, we're considering that we have 3 kinds of paint and 2 types of toy cars. And what the child has to do is choose one color of paint and one type of car. So if there are 3 different colors of paint, red, blue, and green, that can be used to paint 2 types of toy cars, race car or police car, then how many different toys can there be? And so we see, and I have it laid out here in a table format, that we can look at, for each color, each of the 3 colors, there are 2 types of cars. So we see that there are 3 times 2, or 6 possible toys: red race car, red police car, etc. So in the table form, we see that it's the number of ways of choosing the color times the number of ways of choosing the car type. We can also look at the same set of choices using a tree diagram. And here we go. The first choice is color, and the second choice is car type. We would end up with the same number, which is 3 times 2 is 6, if we made the car type first and then the color. But this is how I presented the problem, so that's how I laid it out. So this is an example of the multiplication rule of counting. And this applies, and it applies to this situation. In general, if a task consists of a sequence of choices where there are P options for the first choice, Q options for the second choice, and R options for the third choice, so on, then the number of different tasks that you can complete, or the number of different outcomes, is going to be P times Q times R until, you have your choices made. So let's go back to the sandwich making problem again. So you arrive at a friend's house and you have to choose a type of bread, and there are 3 types of bread. So in this case, the first choice is bread, and P is equal to 3. And then you have to choose a type of protein, either one of these 4. So Q is equal to 4. And now you have another choice: lettuce or no lettuce. And that's 2 options. And then tomatoes or no tomatoes. And that's also 2 options. So how many different sandwiches can you make? By the multiplication rule, we have to multiply P times Q times R times S. And we get 3 times 2. I'm sorry, 3 times 4 times 2 times 2, which is 48. Okay, so there are different kinds of counting problems. There are different kinds of details in how the counting is done, right? Or in how we're making our choices as we go forward. And we can look at this distinction, counting with repetition and counting without repetition. So suppose a child is coloring a picture of a shirt and pants, and there are 5 different colors of markers. How many ways can this picture be chosen? Well, in the first choice, the first choice has 5, so there are 5 colors. So he could make the first, maybe the shirts. There are 5 different ways he can color the shirts, and then the pants. There are 5 different ways he can color the pants. So there are, by the multiplication rule, 5 times 5 or 25 ways that the child can color the shirt and the pants. And what I've done here is I've allowed whatever color, so there were 5 colors for the first choice, and 5 colors for the second choice. So I haven't limited what the child can do with the second choice given the first choice. In other words, I'm allowing the child to choose the same color for shirt and pants, or red and red, or blue and blue. Okay, and the other another kind of counting that comes up with the multiplication rules is counting without repetition. So here a child is coloring a picture of a shirt and pants, and there are 5 colors of markers, but the child wants to use 2 different colors. How many ways can this picture be colored? So the first choice, there are 5 options. But then once we choose something for the shirt, then there are only 4 options remaining for the pants, so it decreased. So we have 5 times 4 is equal to 20. 5 on the first choice, 4 on the second choice. Okay, so we're going to introduce this concept of factorial notation. It's going to help us as we get on to more complicated kinds of counting. So the factorial symbol is an exclamation point, and what it means is for an integer n factorial is n times n minus 1 times n minus 2 all the way down. So if this is an example here, 5 factorial is 5 times 4 times 3 times 2 times 1. That's 20 times 6, or 120. And there are some special case. There's a special case that's worth commenting on. We let 0 factorial equal 1, even though we already know 1 factorial also equals 1. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2, or 6, and so on. Okay, so this notation is going to become helpful as we consider more complicated, as I said, more complicated counting problems. So solving counting problems using a permutation. So a permutation is a specific arrangement. So the problem of choosing 1 marker out of 5 and then choosing a second marker out of the 4 remaining is an example of a permutation. A permutation is an ordered arrangement. So something got chosen for the shirt and then something else for the pants. That is different than flipping the shirt and pants color. So an ordered arrangement in which r different objects are chosen out of n total objects, and repetition is not allowed. And so the number of ways of making this sort of these sorts of choices are is denoted NPR, and we are going to work out here what NPR is and how we calculate it. But I should mention that in many calculators, there is an option to do these permutation calculations and combinations as well, which we will get to directly on the calculator, though it's very handy and required that we also understand the relationship to the factorials. So the number of ways of choosing 1 marker out of 5 and then choosing a second marker, a second color out of 4 is 5, choose 4, and we know that's 5 times 4, or 20. And so we want to generalize that now. So in general, since there are n choices for the first, so we're looking for n choices. We have a total of n objects, and we're going to make r choices. So there are n options for the first choice, and then one of those markers goes away, so n minus 1 for the second, n minus 2 for the third, and all the way down to n minus r minus 1. Let me give you an example here. We have in the situation where we were coloring using 1 color for pants and 1 color for shirts and 1 color for pants, n would be 5. And we would have n for the first choice and n minus 1 options for the second choice. And a simpler way to sort of this is kind of complicated and it's a little difficult with this n thing over here. So a simpler way to write the formula for the number of permutations is NPR is n factorial over n minus r factorial. So let's go ahead and try to understand this in the case of the kid, the child coloring a shirt and pants. So we said that would be 5P4, 5 permute 4. And we know the answer is 5 times 4, right? And I'm going to also note that that's the same as 5 factorial divided by 3 factorial, because the 3 factorial part is going to cancel on both of them. And all this gives us is a more concise way of denoting the 5P4. So in this case, we have 5, this is 5 factorial over 3 factorial. Okay, just different ways. These all mean the same thing. Okay, and we're going to use this this factorial representation as we count options here. Okay, so I want to bring forward a colorful example. So we're back to children and markers and all, but suppose a child has 3 markers, okay, and they are a red marker, a blue marker, and an orange marker. How many different ways can they use the markers to color a picture where they choose a different color for the shirt, the pants, and the shoes? Okay, and so this means I have 3 to start with. So in this case, I don't have all 5 markers, I just had 3. So 3 permute 3, because I have 3 markers and I want to choose 3 of them, but order matters. So we count it as a permutation and we get 3 permute 3, which is 3 factorial over 3 minus 3 factorial, which gives me 3 factorial over 0 factorial. Oops, and that would be 3 factorial over 1, or just plain old 3 factorial, which we do know is 6. So that's a special case, and that's the case where the number of objects that are available is equal to the number of objects you're going to choose in a given order. So that's a special case of permutations. Okay. So this kid, we're going to get a little more colorful. So the child has now 5 markers. So here are my 5 markers: red, blue, orange, green, and purple. How many ways can the child choose markers where they have to choose 1 to color the shirt, 1 to color the pants, and 1 to color the shoes? Okay. And so this is 5 markers total, and we're going to choose 3, and order matters here. So it's 5 permute 3. Okay, so it's 5 factorial over 5 minus 3 factorial, 5 factorial over 2 factorial. Okay, and we see that that's equal to 60. And what I did was I laid them out, all 60 of them out into a rectangle here, into a table. And so we have 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In fact, there are 60 different permutations of 3 colors. So, but notice here how I laid this out. Notice that all of the 6 permutations in the first row are different permutations of red, blue, orange. Now, in the previous colorful example, we showed that there should be 6 ways of taking red, blue, and orange and rearranging them, right? So 6 permutations, it's 3 permute 3, 3P3. And that is why there are 6, 1, 2, 3, 4, 5, 6 ways of taking those 3 colors and permuting them into different arrangements. Okay, and so let's see. Now we want to change the example again, right? So the kid likes these, it's doing a lot of coloring with markers. So now instead of coloring a shirt, a pants, and shoes, the child must choose 3 colored markers to bring to art class. How many ways can they choose 3 markers out of 5? And in this situation, order doesn't matter. That is, red, blue, orange would be equivalent to red, orange, blue, because he's going to choose 1, 2, 3 markers and hold them together and bring them to class. And the fact that red is blue is second or blue is third doesn't matter. They're still the same group of markers. So in this case, the whole first row that we were looking at, that whole first row, and there was 6 items, 6 permutations in that row, they're basically equivalent. They all come down to red, blue, orange. So once we decide that order doesn't matter, we can consider looking at these 60 ways, these 60 permutations, right? And we could say that we could break the 60 permutations down into each row. Notice has that property that it's the same 3 colors, but rearranged. So we can consider each row like a subset, and all of the permutations in that subset are really equivalent when it comes to combinations, just grabbing 3 markers and going to our class. So the total number of subsets or the combinations of 3 colors is going to be your 5 permute 3 or 5p3 divided by the number of, in this case 6, the number of columns here. So the number of ways of permuting 3 markers, 3 factorial. Okay, so what we have then is the total number of combinations is going to be 5p3 divided by 3 factorial, and we have a new piece of notation for that. That's 5 choose 3 or 5c3, and in this case that is 10. Okay, so from each, there are 1 combination from each of the rows in the matrix above. So each row was a different 3 colors. Okay. All right. So in general, the general result is there NCR combinations. In general, if we have n items and we want to count the number of ways we can choose R and order does not matter, then there are n choose 3 combinations, and that's n factorial over n minus r factorial times r factorial in the denominator. So I just wanted to compare how to figure out if what the situation you're trying to count as a permutation situation or a combination situation. And for permutations, the order matters. Okay, so it mattered whether you chose red for the shirt, blue for the pants, and green for the shoes, or some other flipping the pants and shirt colors. Would actually end up with different picture, right? So in a permutation, order matters, and you choosing R objects out of n, and no repetition is allowed. Combinations are similar, only order does not matter. You're still choosing R objects and out of n and with no repetition. So there's a classic permutation combination example I want to go over here. So suppose a permutation, suppose a club has 20 people, and they need to choose 1 person for president, 1 person for treasurer, and 1 person for secretary. All right. And so in this case, order matters, because if I choose 1 person for president, if I choose a certain person A for president, person B for treasurer, person C for secretary, that's certainly different than choosing person A for president and then flipping the secretary and treasurer. So C would be the treasurer and B would be the secretary. That would be a different outcome. So in this problem, we have, it is a permutation because order matters, and there are 20 people in the club, and their need to choose 3, and order matters. So it's going to be 20p3, which is 20 factorial over 20 minus 3 factorial. And maybe play in your calculator, see if you can get your permutation button to work. It's 6,840. So a related problem, right? But this is the other classic example is that of a combinations. So suppose a club of 20 people choose 3 people for a committee. So here, order does not matter. For being on that committee, it doesn't matter if you were chosen first or second. They're going to choose all three people, and the three people are going to have the same job. So here we have order doesn't matter. So we're going to use a combination, and we have n equals 20, r equals 3, and 20 choose 3. 20 choose 3 is 20 factorial over 20 minus 3 factorial times 3 factorial. And if you, again, maybe playing the calculator a little bit, that's 1,140. All right, and finally, we'd like to put some of these counting methods to work in calculating some probabilities. So we're going to compute some probabilities involving permutations and combinations. So let's consider this. In a horse race, a trifecta, a gambler must pick which horse comes in first, which comes in second, and which comes in third. If there are 8 horses in the race and every order of finish is equally likely, what is the chance that your one ticket is a winning ticket? So in this case, we know that order matters. And what is the size of the sample space? How many possible permutations of the horses are there? So it's 8 permute 3. Remember, order matters, so we're using a permutation. And we're asking, so the sample size is has size 8 permute 3. And the probability that any one ticket is a winner is going to be the number of ways that one ticket can occur, which is 1, divided by the total number of possible outcomes. And in this case, 8p3 is 56. So for the trifecta with 8 horses and choosing first, second, and third, the probability that if all outcomes are equally likely, the probability that any one outcome would occur is 1 out of 56. Okay, so let's consider another example, and it's another gambling example, a combination example. So Powerball, the Powerball lottery consists of choosing 5 numbers out of 55, and then 1 number out of 42. And the grand prize is given when all 6 numbers are correct. And we're asking, what is the probability that any one ticket with 5 out of 55 and then 1 out of 42, any ticket is a grand prize winner. So here for the 5 numbers out of 55, order does not matter. So you choose 5 numbers, it's a combination of 5 numbers, and order doesn't matter, the order in which you chose them. So the number of ways of choosing 5 numbers out of 55 is 55C5. And you can use that in the calculator, please. And I got this here as 34,787,761. And then there are 42 possibilities for the last ball. So you can choose any 1 out of 42 numbers. So the total number of possible outcomes in the Powerball lottery is going to be this number times 42. Okay, so it's the same. The numerators here, then I multiply that by 42 and divide by the denominator. And so there are 146,107,962 different tickets. And what is the probability that one ticket wins? Well, it's going to be 1 over that very large number. Okay, so I just want to summarize. The multiplication rule counts the number of possible sequences of an item or the number of possible outcomes if a sequence of choices are made. Permutations and combinations count the number of ways of arranging objects. With permutation, order matters. With combination, order does not matter. And we can use permutations and combinations to compute probabilities. All right, I hope this helps. I'll see you in the next video.